Welcome to Unit 4. So Unit 4 is going to move us from the single boundary problems to doing multi-unit problems. So we're going to have to learn about boundaries and how we specifically figure out which process we are working on when we're writing our balances. And this is where having a strategy for a problem is going to become very important. So let's talk about how do we do system boundaries for multi-units. So the procedure for a multi-unit process is nearly the same as a single unit process, right? We draw our flow diagram, we label it, we write our general balance equation, we simplify the general balance equation, we do a degree of freedom analysis, and then we start moving through the problem. Now there are some differences with multi-units, and the key difference is that you need to isolate and write your balances on subsystems of processes to have enough equations to solve. You're going to have multiple units now, so unit 1 and unit 2. And you can draw a boundary around each of those and balance each of those, but you can also draw a boundary around the entire thing and balance that. So we always need to know which boundary we are now balancing around. So that's going to be an important difference for multi-units. It's also very helpful to do a degree of freedom analysis around these different boundaries. So whenever you define a boundary, you're going to want to make sure that you can do a degree of freedom analysis because that might tell you where to start solving the problem. So before we dive into drawing those boundaries, I want to introduce two new concepts, and these are mixing points and split points. So a mixing point is where two streams are coming together, and that's what's on the left side of the slide. So two streams are coming together, and that's happening outside of a unit process. So it's not happening inside of a box. It's just two pipes basically in the real world. And so I have what's called a Y pipe here on the bottom of the screen. Grab my laser pointer. There it is. It basically is 2 points come in and 1 point comes out. Now a split point is the mirror image of that. So two streams diverge outside of a unit process. So mixed point and split points are going to be boundaries we can balance about. So that's going to be important for us going forward. Now in real life, you might have a mixing point where you have two different treatments that you're using on air or water or soil, and the streams of those come together at the end because we want one product, not two. So that could be like blending some wells, that could be blending streams of air, things like that. Split point is when you want some of the product or some of the input feed to go different directions. So that might mean we don't want to treat 100% of our water going into our system. We only want to treat 70% of it. So we split off 30% and let it go around. So that's kind of what mixed points and split points are in real life. All right, so let's talk about balances on multi-units. So your industrial chemical processes rarely involve one system or one process. So we're going to define a system as any portion of a process that can be enclosed within a hypothetical box or boundary. So inputs or outputs to the system are going to be the process streams that intersect that boundary. So to date, we've had one process, and we've drawn our boundary around that process. So any arrow that crosses into that box is now a input and output of that particular process. Now that gets different when you have multi-units. So if you look at this little picture, if you draw a boundary around unit 1, for example, the stream that's coming into unit 1, the product 1, and the stream that's leaving unit 1 are the only things that cross that dotted line. So that's going to be important as we go forward. We're going to use an example to walk through this. But I want to point out the different boundaries that we can have for this particular problem. So we have two streams coming together at the very beginning, right? There's two streams coming together. That's a mixed point. We have this unit, which we can draw a boundary around. We have the second unit, which we can draw a boundary around. We have a split point right here where one of the products from unit 1 becomes the feed for unit 2, but also has a product stream. And then we have the overall boundary of everything inside the system. So let's go and write that down a little bit more clearly. So if we draw a boundary around the entire process, the inputs to that process are stream 1, 2, and 3, and the products are stream 1, 2, and 3. There's 3 of them. Okay, if you have a feed stream that's going into that mixing point, the input is stream 1 and 2, the product is just the stream that's going into unit 1. Unit 1 has its own boundaries. The stream splitting point that we talked about between unit 1 and 2 is a boundary. Unit 2 is a boundary, And with each boundary, we're going to want to be careful about what affects the overall process. So if you look at the overall boundary on that previous slide, that split point is now inside of boundary A, and so it doesn't actually contribute. So let's use an example to go over this. Okay, so we have a process labeled where we have 1 and 2. We have a product from process 1, a product from process 2. We actually have 2 products from process 2. We have a mixing point in the middle. And you'll notice I've labeled each of these with numbers. If you're somebody who likes to color code, this is going to be a great method for you going forward, especially with multi-units. So we have 3 streams whose flow rates or compositions are not known, and that's 3, 5, and 7. And so we're looking for what's in 3, 5, and 7 for this problem. Now we don't know any numbers for any of the other values, but we're going to try and label things and think about boundaries. Okay, we have 2 components, A and B, that are flowing in the system. All right, so we're going to want to draw different boundaries so that we can think about where balances can be formed. Now, the first boundary that we could draw is this purple boundary, and that goes around both processes, and it contains that mixing point. So if you look, 1 crosses this boundary, 2 crosses this boundary, 6, 7, and 4. Those are the only ones that would be involved in a balance on the overall process. Now let's look at the boundary around process 1. The only arrows that cross this dotted orange line are 1, 2, and 3. So if you are balancing process 1, you don't care about 4, 5, 6, or 7. Same idea with process 2. 5 comes in, 6 leaves, and 7 leaves. And then this mix point right here is also a boundary where we would balance 3, 4, and 5. So let's formalize that on the next slide. So we're going to try and write balances at different boundaries. So if we look at process number 1, the only things that cross this orange line are 1, 2, and 3. So if you write a balance on process 1, your only subscript should be 1, 2, and 3. Now let's look at process 2. If we're in process 2, 5, 6, and 7 cross that boundary. If we're at the mix point, which is green, 3, 4, and 5. If we're at the overall boundary, 1, 2, 4, 6, and 7. Okay, so this becomes very important because these numbers that you're seeing at each of these boundaries are the only numbers that you have in your subscripts. If we're looking at the overall boundary, 3 has no bearing on what is crossing that overall boundary. 5 has no bearing on what's happening in that overall boundary. So if you don't know 3 and 5, you're not going to want to balance the mix point first. You might want to balance the overall boundary because it doesn't include 3 and 5. And so that's going to become important. Okay, so if we were to label this flow diagram with a little bit more information, I've added information about stream 1, 2, 4, and 6. So if we're trying to find 3, 5, and 7, how would we do that? Like, what is the boundary that makes the most sense? Let's talk through that. So if we plan out a strategy, what boundary could help you solve for 3? Well, 3 crosses the boundary with process 1. 3 also crosses the boundary with this mix point. Now, I don't know anything about 5 yet, and I don't know anything about 3, which means that process 1, because I know information about 1 and 2, might be a good way to solve information about 3. Now, which boundary can help you solve for 5? Well, either process 2 or the mix point. Now, the problem with number 5 is that we don't know anything about 3 and we don't know anything about 7. So we can't start with number 5. We have to start with number 3 or number 7 because we actually know more information. So if we think about 7, you can use this process boundary on 2 right here, but we don't know anything about 5 or 7, so that doesn't help. But if we look at the overall system, we know something about 1, 2, 4, and 6, which means we can solve for 7. So what that means is for this problem, you would want to use the overall balance to solve for 7, the balance on process 1 to solve for 3, and then you have a choice. You can balance the split point or you can balance process 2 to solve for 5. Okay, so that's what is going on with system boundaries. We need to be able to draw boxes around these different boundaries. Now in class, we're going to go through some examples of how do we draw those boundaries correctly and which things go in and out of those boundaries. They're all single unit problems once you draw your boundaries correctly. So everything that we've learned in our previous units is going to apply to solving these problems, but it now becomes more important to know your boundaries and have a strategy for solving. So I'll see you in class to talk a little bit more about how to draw those boundaries.